So example 10.3.1. So testing the claim of a linear correlation. So is there a positive linear correlation between beer's alcohol content and calories? So we've been asking ourselves this question now through the whole chapter, and we've been building up to kind of this final inferential procedure. So we first started answering that question by looking at a scatter plot to see if it looked roughly linear, which it did, and then we computed a value of R to measure the strength of that linear relationship. We computed a value of R squared to measure the percentage of the variation in y that was explained by x, and we also got the equation of the line that best fit the data that we had. So now, is what we're seeing in the sample data significant enough to say that we think this relationship exists in the population of all beers? Okay, and we're asked to test this at the 5% level. So step one, we're going to state the random variable and the parameter in words. Okay, so our parameter here is going to be the linear correlation between alcohol content and number of calories for all beers with an alcohol content between 4.15%, because that was our x min from the data, and 8.1%, because that was our x max in the data. And again, we don't know that value. That's what our hypothesis is about, our population parameter. Okay, so our point estimate for that is R. And so our random variable R is going to be the linear correlation between alcohol content and number of calories for these 9 randomly selected beers that we have with an alcohol content between 4.15% and 8.1%. All right, so our second step in Phantoms is to state the null and alternative hypotheses. So in this case, we are asked to test for a positive correlation. So that means our alternative hypothesis, oops, we don't want P there. We want this kind of fancier looking P there for rho. Okay, we want to test that rho is greater than 0, and so by default then the null hypothesis is rho equals 0. Always the same parameter, always the same numeric value, and always inequality. And then we're going to test this hypothesis, it told us, at the 5% level of significance. So at the end of the day, we're going to compare our p-value to 0.05. All right. Now, there's a long list of assumptions if you were to take a full course in linear regression, but again, for this intro course, we just want to know, again, the problem states that they have a random sample of 9 beers. And earlier we looked at the scatter plot. So the scatter plot of the data looks roughly linear with no outliers. So for this course, those are the only 2 conditions that you need to check. So our 2 conditions are checked out to use the linear regression t-test. So we're going to name the test that we're going to be using. So that's going to be the linear regression t-test. And so our next step in Phantoms is the test statistic, but we first start with our statistic. And so again, we're testing rho, which means our statistic is R. And so again, we would enter 2 lists of data. In this case now, what we highlight next to rho, we do need greater than 0. Because this, again, our alternative hypothesis is that rho is greater than 0. So we need to highlight the greater than 0 in this case before we hit calculate. And now on this output screen, we're going to be interested in quite a few values now. We're going to be interested in this t-score, so our test statistic, this p-value, and way at the bottom here is our value of R, so our statistic. Okay. And on the output screen, if we were to use StatCrunch, we would be, here is our value of R, and then when we're doing our hypothesis test, the p-value we want here is the one that's actually, it says it's next to the slope, because instead of doing a hypothesis test about the linear correlation coefficient, we could also do a hypothesis test about the slope. Okay, if the slope is positive, if the graph goes up from left to right, the linear correlation is also positive. And the same thing, if the graph goes down from left to right, it would have a negative slope and would have a negative value for correlation. So here's our p-value, and again, also that test statistic is also given here. So R, no matter which screen we're looking at here, is about 0.913. Oops, 913. And our standardized score for that, to count standard deviations away from the center, we would take that value of R and divide by the standard deviation of that random variable, which is given to be 1 minus R squared. So again, in this case, the value of R squared is also displayed here, so we're just going to take that value of R squared, which is 0.83437513. And up here, if we were going to use this in a further computation, we would keep all those decimal places in there. And then divided by n minus 2, and our sample size here was 9. Okay. And then we're just going to cheat and get that off of our output screen. So again, whether we look at StatCrunch or the previous one from the calculator, test statistics, we typically round off to 2 decimal places, so this is going to be about 5.94. Okay, so this means that the value of R, this 0.913 that we had here, is about 5.94 standard deviations above, since it came out positive, the hypothesis value in the null hypothesis. Okay, so again, if we know something about statistics, which hopefully we do now that it's like week 13, that's really far from center. Okay, we usually expect things to be no further than like 2 or 3 standard deviations away from center, so this is really far, which means we should expect a really tiny p-value for that tail area. So step 6 in Phantoms is to obtain the p-value and to make sense out of all these numbers with a picture. So the p-value, go back to the calculator, was about 2.884 times 10 to the negative 4, which if we round that off, and is also the one given in StatCrunch, that gives us about 0.0003. Okay. So as we're looking at our sampling distribution for R, again, the hypothesis test rho is claimed to be 0, so we would expect a value of R near 0 in our sample. T-scores are always centered at 0. So in the middle of the graph here we have zeros for both. Okay, the value of R in the data was 0.913, so that's off in the right tail. And the corresponding t-score that went with 0.913 was 5.94. And then again, the p-value is this tail area here, which is roughly about 0.0003. So keep in mind, we're going to then compare that to the value of alpha, which was given to be 0.05. And so this p-value is either less than or equal to 0.05, or it's strictly greater than 0.05. And it is much smaller than 0.05. So in this case, our p-value is less than or equal to alpha. So when we go to make a decision now in step 7, we're going to say that since this p-value is less than or equal to 0.05, we would reject HO. And if we state a conclusion in the context of the problem, if we reject HO, we do that because we don't think it's true. So we throw that out, which means there is evidence to conclude HA in context, which in this case says rho is greater than 0. So we're going to put that back with the context of what the variables were and what we're looking at here for the population. So there is enough evidence to show that there is a positive linear correlation between alcohol content, that was our X variable, and number of calories, which was our y variable. And again, inferences we're concluding for the whole population, so not just the 9 beers we looked at. Okay? In all 12-ounce bottles of beer with an alcohol content between 4.15% and 8.1%, because again, that was our X-min and our X-max in that sample of 9. So the model that we formed for these 9 beers, okay, we only know it fits well for beers with an alcohol content between 4.15% and 8.1%.